third part of the matrices and determinant. We have learned the singular, non-singular equation, the adjoint of a square matrix, what are the properties, how to find out inverse of a matrix, and its concerned properties. And today we are going to end up the session. We are going to wind up the whole course and this unit by looking forward for the solution of simultaneous linear equations. So this is our last topic. So let me go to the slide. Solution of simultaneous linear equation, the matrix method. Correct. So obviously, when we are talking about the simultaneous linear equation, so there are various methods might be you have learned or you are aware of. But here, since we have learned regarding the matrices and determinants, so we are going to find out the application of the same. We are going to find out that if we have a solution to be obtained for the linear system of equation, and here we have taken 3 cross 3. It could be any, it could be 2 cross 2, 4 cross 2, or any. Just for the visualization and to demonstrate that what type of method is it and how we are going to implement it, we have considered a 3 cross 3 system. And why we are saying 3 cross 3, but actually it is looking like equations, because when we will write down the matrix related to it, it will be actually 3 cross 3. So if we write down in the matrix form, we can write it down like this. Here we can see the coefficients. The coefficients are A1, B1, C1, and this is for X, Y, and Z similarly. So if we talk about how many variables are there, so we are looking for the 3 variables X, Y, and Z, for which we are going to obtain the solution. And whatever the coefficients, there we are going to take it as a metric system. So here we have A1, B1, C1, A2, B2, C2, A3, B3, C3. When we are working with the numerical, obviously it will be the numerical value. So this is a matrix that we have written, followed by the unknowns. We have unknowns X, Y, Z, and we are aware of how to find out the product. So here the expressions was actually given, and we have written as a product of the two matrix system. And one is our 3 cross 3 matrix, which we normally represent by capital A, and then we have X, capital X we denote for the unknown variables, which is a column matrix. And finally, we are getting again a column matrix on the right hand side, which we represented D1, D2, D3, because ABC notation we have already taken. Right? So this is the normal notation. We used to take that A is our coefficient matrix, X are the unknowns, and B is the right hand side, the values which are known to us. So how we are going to find out? The first thing is we are saying that if A is not equal to 0, then A is non-singular, and then only A inverse exists. Right? So obviously we need the A inverse to find out the solution. So we are looking for when A inverse will exist. So we know that A inverse will exist when the matrix is non-singular, because if determinant, I think here it should be determinant. So notation is not coming properly. It should be determinant of A not equal to 0. Okay? Because then it is non-singular, and we can say A inverse exists, and if A inverse exists, we can write it down the system by multiplication of A inverse on both of the sides. So if I multiply A inverse on both of the sides, what we will get? I will get A inverse into AX is equal to A inverse B, because we have written AX is equal to B. So here we are going to take A inverse on the both of the sides. Now if I open it by the property, we know that A inverse AX can also be written as A inverse A multiplied by X. Correct? So we can write it down like this. And by the property of inverse, we know what is the value of A inverse A. It is IN. If I is an identity matrix of order n, it is n order, means whatever the order of your matrix A, we are going to take the same n. That identity will come here as a result of the product of A inverse with A. So what I will get? I think it's opposite thing. It's not a correct one. So if I write down what we have I into X is equal to A inverse into B. So from here what I can say, we can write down X, because X is an unknown to be obtained. Correct? So, and we know identity into X remains X. So what we can say, X is equal to A inverse B, or we know that how to find out A inverse. A inverse can be written as adjoint A divided by determinant of A. So here we have adjoint A divided by determinant of A into B. So this is our expression for A inverse, and if I multiply it with B, so we will get the value of X. And what will be the X? X is not a value, but actually it is a matrix. Correct? We will get the three values as X, Y, and Z, which are the unknowns. So there we have taken small x, y, and z for the unknowns representation, and here we are taking this as a solution of the given system of linear equation. Correct? So let's see what are the important results regarding this. I think you must be now aware of what is the procedure. Whatever the system of linear equation will be given to you, you have to first write it down as A into X is equal to B, where A is the coefficient matrix. Here also we have been given, so you can go through this. A is a coefficient matrix, X is the unknowns that we are looking for, and B is the right hand side, the given values. And on taking A inverse on both the other side, we can take X is equal to A inverse B, and we know what is the formula for A inverse, adjoint A divided by determinant A. So using the previous knowledge, we can find out that what is the unknown column matrix. Okay. Now here what we are saying is an important result. We are saying that if A is a non-singular matrix, because obviously we can find out the solution when the A matrix is non-singular. You know, it might be if it is singular, we are not getting the solution. So here we are saying A is a non-singular matrix, then the system of equation Ax is equal to B has a unique solution, and given by X is equal to A inverse B. So what property it's written over here, we're talking about the unique solution. It's not so that you have obtained some other values or the unknowns and I'm getting the different one. If we are using the same procedure, the solution should be unique one. The second, we are saying that if A is a singular matrix, if A is a singular matrix, now here we are talking about the singularity. Singular matrix means determinant of A is 0. Okay? If A is a singular matrix and adjoint A into B is 0. Now, from where we are getting adjoint A into B? Here you can see in this expression. Adjoint A into B. We are talking about this. And what we are saying, it is singular, it means this is also 0. And now we are talking about the numerator part. Correct? So let's move on. Here what we said that if A is a singular matrix, let me write down here for the clarity, because here we have already X is equal to A inverse B. So let me write down adjoint A into B, because A inverse can be written like this. What we are saying, if A is singular matrix, then obviously determinant of A is 0, and we are saying this is also 0, means we are getting 0 by 0. Then the system of equation is consistent with infinitely many solutions. If this is the scenario that adjoint of A into B is 0 and the determinant of A is also 0, then we will say there are infinitely many solutions. Infinitely many solution means whatever the solutions are there, they are infinite in number. Whatever the pairs we are talking about, a lot of pairs are those which satisfy the given equation. And the third, we are saying that if A is singular, but adjoint of A into B is not equal to 0. Here what we are saying in the second one, that it is equal to 0, adjoint of A into B. Now we are saying that A is singular and adjoint of A into B is not equal to 0, then the system of equation is inconsistent. Inconsistent means the system is not solvable. So in this case, we can say that system is insolvable or inconsistent, meaning we are not able to find out the solution. So when it is not possible to find out the solution, we can't comment on the how many solutions are existing. Right? Because here the numerator part is 0 and the denominator part is not 0. Obviously, when we solve it, we get division by 0 type of error. When 0 by 0 was coming, as in the second part, we can say that it is indeterminate form, the word we can use. So let's start with the example. Here we are saying using matrix method, we have to solve the system of linear equation. Correct? So we can just imagine that if I am not aware of this solution by a metric system, how we are going to solve, then we use the approach that here we have x, 2x, 3x, and let us multiply the first equation by 2 and subtract the two equations to find out relation between y and z, multiply the first equation by 3, subtract from the third equation and find out the relation between y and z. And when we will have two equations in two unknown, we have to solve them again and find out the value of y and z. So that is also an approach. But here, since we are using the matrix method, it's very easy that we have to write down the system as a into x is equal to b. So a means whatever the coefficients are coming for x, y, and z, the unknown. So we have 1, 2, minus 3, 2, 3, 2, and 3, minus 3, minus 4. And the right hand side is minus 4 to 11. Correct? Unknowns are x, y, z. So now we need to find out the inverse, because here we have the system of form a x is equal to b. And if I find out how we can find out x, obviously it can be obtained by a inverse b. So we have obtained the first thing to find out the a inverse is to find out determinant of a, because if determinant of a is not 0, then only we can find out the value. If it is 0, obviously either it has infinite number of solution or there are no solution. We can say the system is inconsistent. So here we have obtained determinant of a, which is coming as 67. So a inverse exists, and then we have obtained the cofactors to find out the a inverse, because we know a inverse means adjoint a divided by determinant a. And how to find out adjoint a? It is the transpose of cofactor matrix. Right? So here it is very openly written whatever the cofactors are there corresponding to each and every element. Writing out these and finding out its transpose, we have obtained the adjoint of the matrix, and then we have a inverse as adjoint a divided by determinant a, and determinant was 67, so we have written it as such. And the final solution of x can be obtained by multiplying a inverse with b. So here we have written which two matrix we are going to multiply, and hence to find out the solution. So here you can see 1 by 61, 67 was outside, and we have multiplied the two matrices, and on the multiplication of the two matrices, we are getting 201, minus 134, and 67, which is a column matrix. And now, as 67 was outside, we have divided the three values with 65, 7 to get 3, minus 2, and 1. Right? So we are getting column matrix with 3 elements. And on the left hand side, we also have x, y, z. So what we can say that on comparison of the two, we can say x is equal to 3, y is equal to minus 2, and z is equal to 1. So this is how we have solved the given system of simultaneous linear equation. Right? Let's start with the next example. So the procedure is clear that we have learned. Okay? Because here the question is coming, either the question will come directly to find out the system of solutions given system of linear equations, or sometimes we can ask for that if this is the system of equation, then find out which type of solution is coming. So here we have to comment regarding that we are getting a unique solution, infinite solution, because there is a chance. No? Because we have seen the three properties, and according to that, obviously there is a chance of getting a different type of solution. Or the third possibility is the solution can be provided to you, and then after one can ask you regarding the any missing value to be obtained. Right? So that is also possible. So here we have the simple question that we have to solve the given system of equations. So what we have to do? We have to write down how we can find out the coefficient matrix, the unknowns, and the right hand side. So it is a into x is equal to b. Given that equations, you can see 1, 1, 1, 1, 2, 3, and 1, 4, 7. From the three equations, x, y, z we have written in a column form, and the right hand side is 6, 14, and 30. So it is ax is equal to b. Again, what we have to find out? First, we have to find out the determinant, because if determinant is 0 or non-zero, based upon this, we can say the inverse will exist or not. Okay, here you can see that in this case, the determinant of A is equal to 0. So it means inverse will not exist. So what we have to find out? We have to find out the cofactor matrix and to see whether adjoint is coming or not. Correct? So here we have where after obtaining the cofactor matrix, transpose of cofactor matrix is given as adjoint A. And if we have multiplied adjoint A into B, what we are getting is it's also coming as 0. Now you remember what we have learned, because these are the three cases that we are discussing about. That sometimes it is directly that we are finding out the values, and sometimes it is possible that we are getting either inconsistent solution or we are getting infinite number of solutions. Right? So here if you see, we have adjoint of B is 0 and determinant was also 0. So what we can say? Here nothing to be done. Directly we can comment that since determinant of A is 0 and adjoint A into B is also 0, so the given system of equation is consistent with infinitely many solutions. Or we can say this equation of system has infinitely many solutions. Right? So what we have to do, because till now we have just learned that there are infinitely many solutions, so how to show it? This is the next step. Correct? So how we are going to take? We are going to take any one of the variable as k, and we will see how we can write down the two variables in terms of the third one. Right? And sometimes it is possible that one variable is taken as a single variable is taken as a constant, or sometimes it is required to take two variables as a constant and then to find out the relation. So here we can see on taking z is equal to k. Let's go back what the equation we have. We had the equation x plus y plus z is equal to 6, then 14, 30, and we have 1, 1, 1, 1, 2, 3, 1, 4, 7. Okay. So here we have taken x is equal, z is equal to k, and from the first two equation, we have written x plus y is equal to 6 minus k, taking z on this side, and x plus 2y plus 3z was there as 14. So here we are saying x plus 2y is equal to 14 minus of 3k. Now we are not aware of what k is. K is just a constant. Correct? So here if we have to solve this 2 by 2 system, because we have now three unknowns. One, we have assumed that it is equal to some constant value. So what we are getting is, we are saying x plus y is equal to 6 minus k is our first equation, and x plus 2y is equal to 14 minus 3k is our second equation. And now if we try to write down as again as a metric system to solve for x and y, we can take 1, 1, 1, 2 is equal to xy. This is our right hand side. And it is equal to 6 minus k and 14 minus 3k. It is just looking like a 2 plus 2 system. And if we go through it, we have to find it again A inverse. And if A inverse is there, it's 1 not equal to 0. So we have to find out adjoint of A. This transpose of cofactor matrix, and A inverse is adjoint A by A. And here we can see we have obtained unknowns. Here you have not to confuse what is capital X. Capital X here should be X and Y, because we are looking for the values of X and Y as the unknowns. So here if we see A inverse B is written as this. This is our A inverse we have calculated. And what is B? B is the part of the right hand side that we have just written in terms of K. Right? So if we solve it, what we will get is the value of X and Y in terms of Z, means K, that we have already taken. Okay, so this is how we have solved to find out. And you can verify that the value of X, Y, and Z also satisfy the third equation, because we have taken two. You can take any two, and obviously because we are working with a system of equations which are three, it will automatically satisfy the third. So you can choose any two of your choice, because we have taken two because we have to solve for a two unknowns, X and Y, because one we have already assumed to be a constant. Right? So we can see that here, based upon the value of K, I will get a value of X and another value of y. It means k can be anything because we have not restricted what should be the domain of k. Right? So k can be any integer, and based upon this k, we can have the value of x and y. So obviously, that's why we are saying we have infinitely many solutions existing in this case when we have the numerator and denominator coming as 0. Correct? So this is what we have done. So this is all about the matrix system. And we have completed the third part, matrix and determinant, with the last topic of adjoint, singularity, inverse, and then after solution of linear equation. Okay? So that is the whole course. Now let me know if you have some doubts.